So, what does the battery in your phone have in common with the rust on an old car? I mean, they seem like complete opposites, right? One powers our world, the other slowly destroys it. Well, it turns out they're actually two sides of the very same coin, electrochemistry. It's the amazing science of how chemical reactions can create a spark and how a spark can drive a chemical reaction. So here's what we're going to cover. We'll start with the two basic types of electrochemical cells. Then we'll get into the rules that predict how much power they have. After that, we'll see how electricity actually moves through a liquid. And finally, we'll look at the awesome technology it creates and the really, really expensive problems it can cause.
All right, let's jump right in. At its heart, electrochemistry really boils down to a simple idea. You've got some chemical reactions that are just eager to happen. They go all by themselves and give off energy we can use. Then you've got others that are, well, a bit lazy. They won't happen unless we give them a little push with some electricity.
And that brings us to our two main players. On the left, you've got the galvanic cell. Think of this as a chemical reaction that's basically rolling downhill. It happens spontaneously, and as it goes, it releases a stream of electrical energy. This is the hero inside every battery. On the right, the electrolytic cell is the complete opposite. It uses electricity to force a reaction to go uphill, a reaction that would never happen on its own. This is what's happening when you recharge your phone or plate jewelry with gold.
Now, what's really cool is that a single device, like the classic Daniell cell, can be both. Left to its own devices, its chemistry naturally creates 1.1 volts of electricity. It's a galvanic cell doing its thing. But if you hook it up to a power source and push more than 1.1 volts back into it, you literally overpower its natural tendency and force the reaction to run in reverse. Suddenly, it becomes an electrolytic cell. It's the exact same setup, just a different direction for the flow of energy.
Okay, so we know some reactions give us electricity, but how much? Exactly. Can we predict which reactions will be powerful and which will be duds? To do that, we need to dive into the rules that govern a cell's potential. You know, its voltage. You see, all those numbers you find in chemistry textbooks, they're measured under perfect, squeaky clean lab conditions. But in the real world, things get messy. As a battery gets used, the chemicals inside it change, the concentrations shift. So, how do we figure out a cell's voltage then? The answer is this beast, the Nernst equation. Now, I know, it looks a little scary, but it's actually an incredibly powerful tool. That first part, the E with the little circle, that's the voltage under those perfect lab conditions. The rest of the equation, that's just a correction factor for the real world. It adjusts that perfect voltage based on temperature and, crucially, that letter Q, which is just the ratio of products to reactants. As your battery runs down, the products build up, Q gets bitter, and the cell's voltage drops. This equation is exactly why your phone can give you a pretty accurate battery percentage. It's not a guess, it's math. And here's where it gets really powerful. That cell potential we can measure, it's directly tied to two other huge concepts in chemistry. First, it tells us the Gibbs free energy, which is basically the maximum amount of useful work that battery can ever hope to do. It's the true measure of its power. And second, it lets us calculate the equilibrium constant, K, which tells us exactly how far the reaction will go before it just stops. These aren't just three random formulas. They're three different languages, all describing the exact same chemical driving force.
So we've talked a lot about the electrodes, the metal bits where the reactions happen. But what about the stuff in between? How does electricity actually move through the liquid solution connecting them? Because it's not electrons flowing through it like in a copper wire. It's something else entirely.
To get this, we first have to talk about resistivity. Every material has a natural tendency to resist the flow of electricity. You can think of it like trying to run through really thick mud. A material with high resistivity, like pure water, is basically electrical mud. Conductivity, on the other hand, is the exact opposite. It's the paved road. It's a measure of how easily current can flow through something. And in the solutions inside our electrochemical cells, the things that create this conductivity, the things that carry the charge, are ions, those little dissolved particles with positive and negative charges. Now, just measuring conductivity can be a bit misleading, right? Because a really concentrated solution is obviously going to conduct better than a weak one. So, to make a fair comparison, we use molar conductivity. This basically standardizes everything by telling us the conductivity per mole of stuff dissolved in the water. It answers the real question: just how good is this particular chemical at conducting electricity? And this leads to a super interesting, kind of counterintuitive effect. As you dilute a solution, add more water, the overall conductivity goes down. That makes sense. Fewer charge-carrying ions in any given space.
But the molar conductivity, the conductivity per mole, actually goes up. Think of the ions like dancers on a dance floor. When the solution is concentrated, the floor is packed. They keep bumping into each other and can't move freely. As you dilute it, you're opening up the dance floor. Each individual ion has way more room to move, so each mole of ions becomes a much more efficient conductor of electricity.
So what if you had an infinitely large dance floor? What's the absolute maximum molar conductivity you could get at infinite dilution? Well, Kohlrausch's law gives us this really elegant answer. It says that at that point, with no interference, every single ion moves independently. So to find the total conductivity, you just add up the individual conducting power of the positive ion and the negative ion. It's a beautifully simple rule for what seems like a really complex system.
All right, enough theory. Let's get to the good stuff. Let's see how all these ideas, cell potential, conductivity, ion movement, come together to literally power our modern world. When it comes to batteries, we can basically sort them into two piles. You've got your primary batteries, which are single-use. The chemical reaction only runs in one direction. Once the chemicals are used up, that's it. You throw it away. That's the alkaline battery in your TV remote. Then you have secondary batteries. These guys are rechargeable. Their chemical reaction can be reversed, just like that Danielle cell, by pumping electricity back into them.
A perfect example of a secondary battery is the good old lead-acid battery in your car. When you turn the key, a reaction kicks off. At the negative side, the anode, solid lead gives up electrons. Over at the positive side, the cathode, lead dioxide takes on electrons. And in both places, they react with the acid to form the same thing, lead sulfate. As this happens, both electrodes get coated in this stuff, and a powerful surge of electrons is released to start your engine.
Now, fuel cells are a whole other level. They're like a battery that never, ever dies. Instead of sealing a limited amount of chemicals inside, you just keep feeding it fuel, like hydrogen gas, and an oxidant, like the oxygen right out of the air. The result is a non-stop, super efficient conversion of chemical energy into electricity, and the only thing that comes out the other end is water.
But for all the amazing things it does, electrochemistry has a dark side. Because sometimes these tiny little galvanic cells pop up all by themselves, right where we don't want them, and they start to slowly eat away at everything we build.
And this brings us back to our original question. Here's the twist. Rust isn't just iron getting wet and turning brown. The process of rusting is a full-blown, functioning electrochemical cell. A single drop of water on a piece of steel can create a tiny, short-circuited battery that powers its own destruction.
So check this out. At one spot on the iron, which acts as the anode, the iron atom gives up its electrons and dissolves into the water drop. Those electrons then travel through the solid metal itself to a different spot, the cathode, where they react with oxygen from the air. The dissolved iron ions then react some more to form that flaky red-brown stuff we all know as rust. The metal itself becomes the wire connecting the two halves of its own destructive little battery. It's crazy. And this leads us to a really powerful final thought. If the problem, rust, is caused by a natural, unwanted electrochemical cell, could the solution be a controlled, man-made electrochemical cell? In other words, can we use the very same principles that cause corrosion to actually stop it in its tracks? Now that's a question that has launched entire fields of engineering, and it all comes back to the fundamentals we've just talked about.